Morning. How are you guys? Okay. So today I have my microphone working, and I even have a backup in case that didn't work, but got it fixed. I have one concern. I was talking to my wife last night and just telling her about the lecture conditions, the HEPA filters and stuff, and she's like, you know, you're pretty soft-spoken, and when you try to project, you sound angry. Like, are the students just gonna think you're angry all the time? And I don't know. Do I sound angry? Okay. Maybe it's just because when I do try to project, my wife's not used to that, so it just sounds angry. Um, so hopefully, I guess maybe you guys get to know my angry voice as if it's not angry, and then there you go. So anyway, um, I don't intend to be angry if I sound angry when I'm trying to speak loudly. So there's that. Okay. Anyway, last time we talked about reactors, and we were kind of working on mass balances in reactors, and we were making some progress, kind of talking about these three different types, and essentially for each of them, what we said was the accumulation rate is always going to be what's equal to it's going to be equal to the inputs rates minus the output rates plus whatever kind of reaction rates we've got going. So if we were to take a look at the batch reaction, we really have no inputs and no outputs. So whatever total accumulation we have, which, by the way, we will typically write that as dc dt, or maybe dn dt if we're talking about some number of stuff. In this case, that's just going to be equal to the reaction in a batch scenario, right? Then we said, okay, well, in a CSTR, we do have inputs and outputs, and usually that's a flow rate times some concentration. And what's coming in is usually what we'll say is the C naught being the initial before the treatment step, and then the C out would be just QC. So something to that effect, and then our reaction term. And last time we were taking a look at the reaction terms a little more closely, so we're going to come back to that and put these two pieces together in terms of what type of reactor we have, plus whatever reactions are going on inside, to give us some indication of like how to really write that mass balance equation. So, and this would be plus or minus whatever reactions we have, right? So, in the case of a plug flow reactor, I mentioned that it works a lot like a batch reactor, and we'll go through each of these cases in a moment, so I'm going to kind of backtrack just a little bit here. In a plug flow reactor, we said that we can think of it as a little snippet of water that's flowing through, and basically in that little block or plug of water, we just assume that it's perfectly mixed in there. So inside that plug, it's perfectly mixed, but it's also very narrow. So it's just a small little plug and lots of small little plugs flowing through all at the same time, and each one we can consider as a batch reactor. Each one is going to stay in the system flowing through for a certain amount of time based on the distance of the pipe or the reactor shape, right? So for whatever amount of time it takes for it to go all the way through, we would call that the hydraulic residence time. Now, we have hydraulic residence times in normal, a CSTR as well, but in that case, it's mixed throughout the whole system. Whereas this guy, the tau, or in this class, we'll often say theta for the hydraulic residence time. It's just how long the water stays in the reactor. And that's going to be a function of the flow rate, how fast the water is flowing, and the volume of the reactor. So literally the hydraulic retention time, and this is one you just commit to memory. You'll have an equation sheet with a lot of the more complex equations, but this one you should know, you should be able to know, just commit it to memory. This is going to be V over Q, because we need to get terms of time, and if we take volume and divide that by a volume per time unit, then we get our time on top, right? The volumes cancel. So it's very simple. Commit that to memory. You'll be using it all the time. If you don't already have that in mind, remember that. And sometimes Sometimes people will call it tau. We'll stick pretty much to theta, but like you see in this little graphic, we have a, well, I guess that's just a T there, but, oh, there's the tau, sorry. So in this graphic, we're saying that halfway through, T is equal to half of tau. T is equal to half the residence time. Then once you're all the way through, T is equal to the whole residence time. That's all that's saying. Okay, so with that, the math for a plug flow reactor turns out to be the same as the math for a batch reactor, as long as you're using the residence time instead of just some arbitrary time, right? Because if I have my water bottle and I say I'm going to shake it for 5 minutes and that's going to be my reaction time, that's a lot different than saying I'm going to take this little batch reactor, put it on the escalator, and the amount of time it takes to get to the top, that's the amount of time. That's maybe half a minute or something, you know. So it just depends on how long it takes for it to go through the process. Okay, so with that in mind, let's take a look. And I just introduced hydraulic residence time. I do have a visualization for that. I'll pull up in just a second. So the hydraulic residence time, I just stressed it. I'll say it again, and we have the whole slide here. This is really the key design parameter for almost all of our systems in terms of the mass balance parameter, because, I mean, sure, there's other things that can change, but this is relevant for any reactor where you've got a flow rate. Okay, so we're going to constantly be seeing it. There's a few things to consider about non-ideal reactors. Can certainly be affected if there's not perfect mixing, or if there's some issue. This video I'll show you in a second is like a batch reactor, and one thing you can see is that it's mixing more than perhaps it should for it's a plug flow reactor. It's mixing a little more than it should for a true plug flow. So let me pull this over. So we see here, dye has been added to this little stream of water that's flowing slowly through around this bend. And this is actually what a plug flow reactor would probably look like in real life, something like this, where you've got these baffles here to section the flow and cause it to go through like a snake-like motion to get to the end. So in real life, this is more realistic than just having like a pipe or a hose. Technically, a pipe or a hose might be a better CSTR or a plug flow reactor. But you can see here, we've got spots where there's some of the concentration of this dye is leading ahead. Some of it's pooling up in a higher concentrated spot over here. There might be some spots where it's just kind of looks like it's not even been mixed at all. Whereas an ideal plug flow reactor would be like, you'd have uniform concentration throughout here, and then that would go all the way through. So right here we can see this should have the same concentration all the way through right there, but it doesn't. So this is kind of an example of kind of a plug flow reactor, but also looking at the non-ideal cases. For the most part, we'll be dealing with ideal. We could get into non-ideal, how to model that, how to adjust for things. Maybe you take, instead of one plug flow reactor, it turns out if you take an infinite number of CSTRs, where you have a little well-mixed spot, water coming in, and then going out, and then another well-mixed spot, that math also comes out to be the same as a plug flow reactor. So if, instead of taking infinite, maybe take 5. Maybe one area here is pretty well mixed with itself, flowing into this next area, flowing into this next area. You can kind of model things like that, having somewhere in between. So we will take a look at combining reactors in light of that, or in light of just processes that have one type and then a different type, or maybe repeated of the same type of reactors. So we'll do some stuff like that as we go. So I wanted to show you that, and you can kind of get a feel for that residence time in that video, you know, how long that video is lasting. that's about the time it takes for that water to flow through most of the reactor there. That was also a good example of what we call a tracer test. Again, talking about non-ideal reactors. If we want to know what happens in reality, we modeled it maybe after like the perfect ideal reactor, but in reality we know things aren't perfect. Well, tracer tests are a good way to do it. You don't normally build a reactor with clear plexiglass chambers and keep it completely clean so you can see everything, and add dye so you can visibly see it. Normally what happens in a reactor is it's a black box. You have some assumptions, you build it, it's concrete, and maybe you have a little window to look through, but you're not adding a bunch of dye into your water that people are going to drink, right? So normally we don't have much information. So what we do is we inject something that is okay to drink, in fact, perhaps adding some health benefits, and trace that as it goes through. That thing I mentioned is fluoride, typically. So fluoride in the right concentrations has a great dental health benefit. Too much of it can be a big problem, but we often add it for both use as a tracer test and also just a generic benefit it provides to our, the population that's using that drinking water. So that's one example. And fluoride doesn't really react too much with anything in those systems, so that's another reason we can add it. We expect there's no reaction, and so then the information we get out of the tracer test is pretty much all about the hydraulic parameters and not about the reactions that could be going on because it doesn't react. It's pretty easy to measure. So thinking about it in terms of our mass balance and stuff like that, if we have no reaction, then measuring the concentration over time is going to tell us a lot more about just the flow rates. And if it's not an ideal reactor and we're not sure exactly how much the flow is actually coming through, maybe some of it's going faster than other parts like we saw, we get a lot of that information out by using a non-reactive tracer to test with. So, okay, with that, let's take a look at some mass balances. And for the batch case, we'll take the first one. We'll say that, again, our accumulation rate we can describe as dc dt. And that's going to be equal to the inputs minus the outputs plus whatever reaction's happening. So we'll do a couple examples here. Remember, for batch, the first thing you ought to do is draw the system. Remind yourself what the system looks like. So a batch case, we've got some jar of water. It's stirred, perfectly mixed. This is going to be an ideal reactor. That's all it is, right? It's some water in the system, and it's going to sit there for some amount of time. So, with that in mind, see if you can take the first steps for deriving a governing equation for a zero-order decay reaction in a batch container. So, derive it so that you have some way to measure C, or to find C, okay? I'll walk you through it in a moment, so just give it a moment to engage your brains there. All right, so for this zero order decay, I have written here the general equation for the rate. So R of C, the rate at which C is going to change, we could say that's simply dc dt. So that's also going to be our accumulation term. And so we're going to say our accumulation term is equal to the inputs, 0, outputs, 0, because it's just batch. There's no flows coming in or out, plus whatever reaction's happening. And then we know that in this case, we've got a zero order decay reaction. So that means it should be minus k times C to the 0 power, because it's zero order, right? So before we even proceed, we can also just note to ourselves that the units for K are going to be whatever unit's concentration is, maybe milligrams per liter per time. So K would be something like milligrams per liter per second. So if we needed to do, if we had an actual problem to solve here, that would be a good thing to write up and confirm there. Okay, so then what we end up having here is this differential equation is very simple, right? So dc dt equals minus k. So we can do separation by parts. dc equals minus k dt. And then we can integrate. Okay, I mentioned we have a little bit of calculus to do in this class, but it's stuff that you will remember. So here, we're going to integrate from the initial C to the final C. And over here, we'll integrate from time equals 0 to time equals time. If this was a plug flow reactor, we would do it to time equals tau. Sorry, I'm in the way. Okay, so with that, if you remember, this is just simply on the left going to be C minus C naught. And on the right, this is going to be minus K times T minus K times 0, right? So just minus K times T. So we now have an equation void of any differentials or anything weird like that. And we can then find C by saying C equals C naught minus KT. Okay, so that's zero order decay. Does that make sense? Kind of follow that? Okay, awesome. So that's a pretty simple one. We could do it for growth. And in fact, I would encourage you to, if you're going to come back to study this, maybe trying on your own, you could do this with a growth equation. And it's going to look very similar, but of course you'll have a difference there in your starting condition where this negative will be a positive instead, right? And then that changes the math a little bit, but not a lot. Okay, so take a moment and start thinking about how you would approach it for the first order. There's a slightly different calculus step required, something that you'll probably remember. You'll definitely remember it once I remind you, if you don't already. Okay, so if you're thinking back on calculus and differential equations and all that, maybe you'll remember that kind of like we did last time, we can actually do the integration by parts, put the dt on the other side. So we can do that here too, but in order to integrate with the c term there, we actually kind of need to get it on the same side as our dc. So we're going to do the dc over c equals minus k dt. So the right side is pretty much the same as it was over here, k minus k dt. So we'll integrate both sides again. From 0 to t. And on this side, we'll take that integral from c naught to c. Now, on the right-hand side, of course, that's just going to be minus kt again. On the left-hand side, this is where I'm expecting you may have to jog your memory. So assuming you've got to this point, essentially what we're looking at is the integral of dc over c, and that you might remember that the integral of 1 over x dx is something you've seen before in calculus, right? So this integrates to the natural log of x, and if you take it from, that's from 0 to x. If you take it from, let's say, x naught, then you get natural log of x minus the natural log of x naught. Okay, so that's the piece of memory that I'm reminding you of from calculus. You probably learned this some time ago, and then maybe haven't used it in a while. So with that in mind, then we have over here the natural log of c minus the natural log of c naught. There's one other memory trick here, or thing to consider, and that's one of the natural log rules. This can simplify kind of nicely if we remember that the natural log of something minus the natural log of something can also be written as the natural log of that first thing divided by that second thing. And suddenly, this is going to look a lot like something you learned way back in Algebra 1, and we've talked about already in terms of interest rates. So if we take this, the natural log of c over c naught equals minus kt, and then we decide, okay, well, we were trying to solve for c here, as sometimes maybe you'll solve for k or whatever, but if we try to solve for c, maybe it's going to be easier if we don't have the natural log there. So we take e to the power of both sides to get rid of that, and we're left with c over c naught equals e to the minus kt, and you could rewrite that as c equals c naught times e to the minus kt. Something you've seen many times before in various contexts. And it's a little bit universal because, as you just saw, this is a first order decay reaction. So this is, something you've seen a lot before. Now, hopefully you have a better grasp of how to derive that from that governing principle of the mass is going to stay constant. There's no creation or destruction of mass in the system. And if you have a simple system like this and a decay reaction, that's just what's going to happen. I say decay reaction, it sounds like it must be chemistry or something, but really, like interest rates, that could be a reaction. So you'll see this in a lot of places where you have some change of something that's dependent on how much of that something you have there, right? So maybe it's this K then might be like your interest rate of, you could kind of talk about it as an interest rate constant to be precise, right? So this would be your like 5% interest per year. And then that depends on how much money you have in the bank, which is your C, right? It'll depend on how much you started with, your C naught, and as you continue to grow it, then it will continue to compound, and then because it's a percentage of what you have there, that's that first order kinetics. Whereas, so if you take a look at, C after 10 years, if you started with $10, you could calculate that. That's going to be a lot different if you had a zero order rate, which does not depend on how much stuff you had in there. It's just going to be, okay, C your amount of money you have after 10 years is equal to, how much you started with. In this case, so plus if you're adding or minus if you're subtracting. Maybe you get $5 per year. Then it's just 5 times 10, and there you go. So this explains that difference between the exponential versus kind of a linear growth. Okay, so that's in the batch reactor case. So I have that note here. Just a reminder, this is the same for the plug flow reactor, except instead of some arbitrary time, you have to find or make sure you have the hydraulic residence time. And I'm sorry that the scribbles are blurring that. Okay, for the CSTR case, again, it's going to be similar. And for this case, one thing I'll do, we'll walk through it as well if we have a non-steady state system. But for the moment, let's assume we have steady state, okay? Again, the first thing I recommend is draw your system. Label the inputs, outputs, that type of thing. Make sure you're confident that the system you are actually writing an equation for is what the question is asking you for, right? So CSTR, you've got an input and an output, Q, C naught, and Q times C. Inside the reactor, this is going to be C. We'll talk a little more about that in a little bit. But because it's mixed instantly, that's just C there. And you have some volume here too. I'm going to edit my slides for a second. Don't mind me. Just worked on that zero order decay in a CSTR. All right, so here again, I start off giving you this, just the generic rate equation. So the rate component, dc dt equals minus kc to the 0 power. This is describing what goes into this spot. Now, last time when we were doing the batch reaction, it didn't really matter. We didn't have to think anything else of it because there was no in, there was no out, and we had dc dt there. In a CSTR, since we've got this system here, this term is going to go inside our bigger equation as one component of it. And so the larger equation, really, we always are starting with this. We did so in the batch reaction as well. It just maybe didn't feel like it because it was so simple. Okay, so we can start with the dc/dt for the entire system is 0, because I said it's going to be at steady state. And that's going to be equal to what's coming in, QC0, minus what's going out, QC, plus whatever reaction we have going on. That's going to be our reaction term right here. Okay? So plus minus K times 1, because C to the 0 power is 1, right? So I'll just leave that as minus K. So while I wrote out the rate here for the reaction of C, this is still the reaction of C, but if we're looking at the mass balance in the entire system, the rate at which C is going to change in this CSTR system, this is going to be the governing equation, the big picture of it. So from here, maybe you want to solve for C, maybe you want to solve for, I'm sorry, I missed something here. This reaction here is also happening in the volume that we have, which is very important. So I apologize. We have to have that volume term because, again, you can check yourself here, which I should have done. This K, that's going to be in, for the 0 order reaction, that's going to be like milligrams per liter per second. But these other terms are just mass per second. This, like the Q times C, that's going to be a volume per time times a mass per volume. So that's leaving us with just mass per time over here. And the way I wrote this at first was a concentration per time with just K. So we need to have that volume to get the terms to be like. So yeah.
So when we're looking at mass balances, if it says like what's the flow rate, should we assume that they want us to find the mass flow rate instead of like the volumetric flow rate?
Okay, so if a question is asking you to find the flow rate, what you're going to be looking for is the Q here, and the Q is going to be a volumetric flow rate. But if it's asking for like what's the mass loading rate or something like that, then it might just be mass per time. Yeah, that's a good question. So, and one thing about these types of problems is you really do learn like, okay, what is it actually talking about? It sounds like it might be this, could also be this. So that's something that it's great to be asking yourself, like, what exactly does it mean, and how can I figure out that? Always, you're free to ask me. On exams, you're not going to be as able to. You can ask for clarity, of course, but that's a great question and a great way to be thinking about it. Like, okay, what exactly am I solving for? So let's solve this one for Q. What I'll do is I'll solve it first for C, and then we'll take a look at what that would look like if we solve for Q. And again, this comes back to, we have this sort of governing equation, but we can use it for some, whatever purpose we want. So in this case, if we want C here, we'll go ahead and put, actually the first thing I'm going to do is I'm going to get rid of the Q's. That'll make things a little easier. So we'll divide everything by Q. And so we have 0 equals C0 minus C minus K times V over Q, and we just learned that V over Q is hydraulic residence time. So that's a nice simplification. So I'm just going to say we're dividing everything by Q here. Yeah. What's that? The reaction, this reaction that is taking place is happening in the entire volume of the thing here. So, and that's what I was noting on because I forgot it at first. It's easy to forget. But in this reactor, you have some set volume that the reaction is occurring in, and so you have to incorporate that. In fact, technically in our batch derivation, I probably should have included it there as well. What I probably should have said was V dc dt is equal to minus k times V, but they cancel, right? So the accumulation in some volume is equal to the, in a batch case, is equal to the reaction in some volume. So in this case, I should have done that to show you that these cancel. And in this next one, we see that in our CSTR, we do have that reaction occurring in that volume, and that's what allows these units to be mass per time instead of concentration per time. Yeah, and one thing you could do if this helps is add that V here in front of this dc dt and keep that V here. It seems redundant, but that might help with this part of it. Okay. So with that, we can solve for C here. Now it's a little easier. We can just say C equals C naught minus K theta. And that would be our equation if we solved for C. Now you could go from here to solve for Q. Although that means we have to extract it back out of here. Maybe it's going to be easier to start from the previous step. Doesn't really matter. It's just going to be algebra. You know, between which thing you're solving for, that's just going to be a difference in algebra requirements. And so in this case, maybe what I'll do is take the Q C naught minus QC and say that that's going to be equal to, you know, so if we took both of these and took them to the other side, or rather just maybe moved this minus KV to the other side, that's going to be minus KV. So then we could say Q is equal to KV divided by C naught minus C. And that would be an expression for the flow rate. So you can see we can manipulate this any way we want now that we have the base equation. Does that make sense? We good? All right, so take a shot at the first order decay in a CSTR. All right, so let's solve for C for this one as well. So hopefully you should have at least gotten to here and then started working on the algebra. So we'll go ahead and do that. So we would set it up. Again, we're doing a steady state system here. So 0 equals Q C naught minus QC minus KCV. So with this, we would say, let's divide everything by Q. And we have C naught minus C minus K times theta. And that's all equal to 0. So we can get our C's on the same side. Say C minus K theta equals C naught. C times 1 minus K theta. We extract those C's. Sorry, I forgot the C there. Equals C naught. And so C would be equal to C naught divided by, did I flip the plus sign there? I feel like I flipped the plus sign. Yeah. Yeah, sorry. It should. Yeah, that's what, like I added it back down here because I forgot. But I also feel like I flipped something. This 1 minus, I think this should be 1 plus K theta. Anybody see my error? Oh, yeah, okay. I took, so we have this C naught minus C, and I took that to the other side. I should have, what I could have done was added this to the other side, added the KC theta. So that would be C plus KC theta, right? Yeah. It turns out if you do a growth reaction, you get a minus there. Okay, so again, here we have an equation for C. You could also see very easily if you wanted a ratio between C and C naught. So a lot of times when we solve a system, we're interested in not just the final concentration, but maybe what percent did we remove, or what fraction did we remove. So then that would be C divided by the initial C, C over C naught. And so what you'll see pretty often is C over C naught equals 1 over 1 plus K theta. And again, one thing I'll note here is you can describe most of the system just by the hydraulic retention time. There's some K for the whatever reaction you're interested in, and then theta. That's all it is, 1 over 1 plus K theta. So it's a lot of the control of a system like this is in that theta. So it's just kind of something to keep in mind. So if we were solving in this form, it would look like that. You'll solve in that form quite often. But you can see very easily you can get from one spot to the other. You could solve this for K, you could solve it for theta. Again, one thing I'll remind you of is it would be worth your time to go through and make sure you can do this with growth equations. You know, I'm pretty confident that you guys could just go ahead and memorize these equations and work from there, associating them with first order decay in a CSTR. You could do that, but I would prefer you master this method so that you're much more capable of handling a different system. Maybe you have 2 inputs, maybe you have competing reactions and you need to add them both into there. Something, you know, whatever the case, it would be better if you could learn this, how to do it. Yeah. Yeah, I'm not planning to give you these particular equations because these are derivations I expect you to be able to do. If I do anything that's more complicated than a 0 or first order based derivation, I'll probably give you an equation or some help otherwise. So in terms of an exam, these ones that I covered for the zero order decay, first order decay, and growth, because I gave you the full spell out here for the decay, but I expect you to also be able to derive them for growth. That's what I'm noting here. It's essentially the same process. This is a skill I expect you to have, and so I don't, like, maybe you'll remember it, and that'll give you something to double check yourself with, but you should be able to do it, because that's the skill I want you to learn, is how to apply these, you know, for different settings. Yeah.
Why are you able to assume that accumulation is zero?
Okay, so the question was, why am I able to assume accumulation is zero? Because I told you so. So what happens if it's not? So let's do a quick rundown of non-steady state. So the steady state assumption is why we said that's zero. So if we're not at steady state, that's, again, like if you have a bank account and you've got some interest rate, you've got income and expenditures, but the total balance in there, like if it's at steady state, it might fluctuate, but over the course of some time period, it stays the same inside, despite adding more, taking out less, and paying interest or whatever. Like whatever is happening, it stays the same in a steady state system. If you have non-steady state, then you're either depleting it over time or you're building it up over time, right? So it's really about the not how much is going in or out. The steady state's not. It's about like the fact that it's accumulating or not for steady state, right? So if it's accumulating one way or the other, positive or negative, then it's not at steady state. That's why a batch reactor with some reaction happening in it, there's nothing else coming in or out. It has to have an accumulation. Either it's growing or decaying. For something that has the inputs and outputs, then then it's a different question. Okay, so non-steady state. And here, what I expect you to be able to do is like these steps of saying, okay, the non-steady state system, we're going to have dc dt, like basically starting from this governing equation, right? For a non-steady state case, this is going to be a CSTR we're looking at. You should be able to at minimum write this out, right? So this is going to be equal to Q. Well, first let's draw it, right? We have some CSTR with a Q in, C naught coming in, a volume, and a Q going out, and a C going out. Technically, the inside that volume is also a C. So the dc dt then would be equal to Q C naught minus Q C. Then we have the reaction term, and this is a zero order decay, so we have minus K in some volume. Okay? And actually, this is going to be, if you check me on the units here, what you'll notice is dc dt, that's a concentration per time, but we need it in mass per time. So we actually have to include the volume that we're talking about, right? Our control volume is basically that reactor. So this is going to be our governing equation. And what you'll notice is for simple cases, the integration is pretty simple. So if it is a very simple integration, I do expect you guys to be able to go forward and do it. But I'm going to be careful and give you help if it is at all more complicated, or maybe just ask you to give me it in terms of dc dt or something. I'm going to be careful if I assign a non-steady state system because they can get complex. So let's work with this for a moment. If we divide everything by Q, seems like a pretty handy thing to do sometimes, then we'll end up with V over Q on the left is theta minus C naught, let's be correct here. Theta dc dt is equal to C naught minus C minus K theta. Okay. So depending on what we're solving for here, we're going to have to integrate for C. So let's say we're going to solve for C here. So dc dt equals, let's say, actually, let's see. We'll just keep going with this. Okay. Let's do this. Theta dc dt plus C is going to be equal to C naught minus K theta. Let's see. So I'm actually a little bit stuck myself thinking about, okay, what do I do with DC plus C? I think that's simple, but I want to double check before I write it out and tell you for sure. We'll look at something in a moment that probably has this written out for us anyway. I think the first order decay, the first order one is going to be a little simpler. I'll write that out and see where we get with it. I just am doing this on the fly. I'm not confident with myself at the moment, so we'll come back. But you should be able to write this out and start getting it towards a form of, oh, I'm going to need to integrate something because we have the dc dt, right? Presumably it's simple. Presumably I'm not thinking clearly. Again, I'm going to give you more coaching and more practice with this if I am going to test you at all on it. Clearly I'm not, giving you enough information at the moment. Point being, hopefully you could write this out, right? V dc dt is equal to Q C naught minus QC plus the reaction, which is minus V K C in this case. And so here, we're looking for this dc dt. I'm just going to go ahead and divide everything by volume this time, see if that's more convenient. Q over V C naught minus Q over V C minus KC. So we'd want the C's on the same term. dc dt plus Q over V times C plus K times C equals Q over V times C naught. So then we would, get it in terms of dc plus Q over V C plus KC. We could extract the Q over V and the K algebraically, and then over here we'd have Q over V C naught times dt, and then integrate. So that would be kind of the approach. And then the integration, of course, in some cases will be simple, in some cases will be complex. That's all zero order and second order. I'm going to skip ahead just a tad. We're going to talk about second order in a moment, something I'm not going to really have you do much at all of. But if we take a look at this table, this is from a different textbook, it essentially gives us the integral form for each of these. And so when we were taking a look at that, let's say the zero order, we had the rate, which was dc dt, so minus k naught. And that's k for the zero order. So dc dt equals minus k. We saw that when we were deriving these. That was our rate form. So in a batch case, this is what they're looking like, right? So In a batch case, that turns out to be C at T minus C naught equals minus KT. We derived that. So this table is kind of showing us that process put into a table. And for first order, dc dt equals minus kc. So when we integrate that, natural log of c over c naught equals minus kt. Now when we do a second order, that's where we go and we have c squared. So if we were to do a second order batch decay reaction, we have dc dt equals minus kc squared. Again, we could put the volume on both sides here. For a batch case, that disappears. And we're left with an integral of dc over c squared equals minus k times dt. And that's where I'm telling you, I'm not going to ask you to remember that integral or how to apply that to anything in that regard or more complex. But there is an integral here that is known, that is well described, and it turns out that that's 1 over c minus 1 over c naught is equal to kt. So we know that if we integrate, again, from c naught to c, from 0 to t, I would give you that table to work with, and then you would say, okay, well, on the right, we know that's dt, kt, minus kt. And on the left, that's when we would go to the lookup table and say, oh, okay, that's 1 over c minus 1 over c naught is the integral. Second order reactions are fairly rare. It's usually something like a radical that can react with other stuff really quickly, and that depends on how much is there. And it can react with itself really quickly, which, again, it's dependent twice then on how much is there. So it's reacting at such a rate that it depends on a square, like the amount of stuff that's going to react depends on how much is there squared. Okay. In a CSTR then, what you would end up having to do is say, okay, V dc dt is equal to, the typical, what's coming in, QC naught minus QC, what's going out, minus VK, or we'll do KV, C squared here, and then solve and integrate that. Okay. I'll plan to come back and touch on the non-steady state systems next time to do a little better job than I did a moment ago covering the simpler cases, because we should be able to do that, and I just wasn't quite prepared enough to walk you through it. For the second order cases, I want you to be able to write this part out at least. You understand where things go from our governing equation. But unless I give you some hints and help, I don't expect you to necessarily know or feel confident going past that. I expect you to know what you should do, not necessarily how to do it, right? You should, if you needed to solve for C, you're going to have to integrate first of all. And that's where I would give you guidance on what the integral is or whatever. You should realize you would need to separate by part, integrate by parts, all that. That process is what I'm interested in you knowing, and the fact that you can apply it to different cases. All right. Is that clear enough for now? We'll come back to the non-steady state systems. All right. So with that, let's take a look at an example. This is from our book. We have a polluted lake. It says, consider a 10 times 10 to the 6 cubic meter lake fed by a polluted stream, having a flow rate 5 cubic meters per second and a pollutant concentration equal to 10 milligrams per liter. So that's this figure down here. There is also a sewage outfall that discharges half a cubic meter per second of wastewater, having a pollutant concentration of 100 milligrams per liter. The stream and sewage wastes have a decay coefficient of 0.20 per day. Assuming the pollutant is completely mixed in the lake, and assuming no evaporation or other water losses or gains, find the steady state pollutant concentration in the lake. So I'm going to give you maybe 3 or 4 minutes to work on that. See if you can get started on it, applying what we learned. Think about what kind of system this is, and see if you can start solving for that steady state pollutant concentration. Yes.
The order of the like
Yeah. Okay. So great question. I was about to start talking about it. So as you take a look at this system, first of all, we have two inputs, and we have some reaction. So I started writing it up. 0 equals QS CS plus QW CW. Those are our two inputs. So you just add both input terms. Then minus the output, which is the QM CM. Then there's a question of the reaction rate, right? How does the rate equation fit in? How can you know the order of it? So we were given some information about the reaction, and what they said was it was a decay rate coefficient of, if I can find of 0.2 per day. So remember, so that means K is 0.2 day to the minus 1. Remember what we said about the rates and the units balance, right? We have dc dt equals K times C to the nth power. And those units have to match. You could say V on both sides, but that's, they just cancel. So this has to be, in this case, we've got milligrams per liter and we're working with like days on this case, I think. Well, there's seconds and days, right? So it could be seconds, could be days. We'll use days here. That's going to equal K times C. So if C is in milligrams per liter, over here we've got milligrams per liter, and then K has to satisfy the rest of it, because these will cancel then, and K needs to cancel with whatever's remaining. So K then this is for a first order, I'm sorry. So if we took C here as first order, then K has to be in per days. So we know if it's per day or per time, that's first order. Yeah. Can you say it again? If it was 0 order, K would be given to us like this. If K was 0 here, we would have no milligrams per liter, and K would have to satisfy all of those units, so K would have to be milligrams per liter per day. Okay, so good questions there. Okay, so yeah, and I was starting to write what K was, and I was going to explain exactly that, so you guys are right on target here. So with that, a few of these things we can just plug in as numbers, but I'm going to stick with them the way we are for just a moment. We need to solve for CM, and I mentioned I was going to talk about this. So in a CSTR, we have an input and an output, and the whole thing is completely mixed. And by the way, the lake, it said everything was mixed. The pollutant just mixed perfectly, right? It's kind of a silly assumption probably, but maybe there's a lot of wind, right? So there's some amount of current here keeping it mixed enough to assume that it's well mixed. That's the CSTR case, right? We have streams flowing in, a stream flowing out, inputs and outputs, and it's a well mixed reactor with some volume. Well, when we talk about the concentrations here, we have some initial concentration coming in, or in this case, two different ones. What's going out is the same concentration that's in here, because if we mix it, whatever's in here is immediately coming out, right? And the way this works is when something highly concentrated enters it, and there's a reaction depleting it, then it's just an immediate dilution. So it's like you're adding a highly concentrated stream in here, but it's a very large volume. And in the volume, that stuff's being depleted constantly. And so it's like an immediate drop of your concentration once you enter it because of the dilution. But that also means whatever's in here is the same thing as what's going out because it's perfectly mixed. So it's kind of a strange phenomenon. And there's some benefit to like having that instant drop, but you also don't get as much decrease as if you had just a plug flow reactor. We'll talk about that more at a later time. Okay, so we're kind of out of time. We'll pick up here next time, and I will solve this with you, and then talk about. At that point, we're going to launch into drinking water treatment as a topic, go over some of the regulations, and then for the next couple weeks, we're going to be dealing with physical processes for drinking water, and then we'll have an exam. Then we'll go into chemical processes for drinking water and disinfection, exam, and then wastewater. Now, one last thing, I do apologize. I have not posted videos. I've not posted notes yet, stuff like that. So I'm a little behind on organization for the class. I'm going to revise the syllabus, talk to you about the plans for makeup or whatever. What I'll probably do for the makeup is just host a live stream from home, either on the weekend or some other time. I'll go over probably the Flint water crisis, which I had planned as a lecture. I'll just take that out and do that separately, something like that, so it's more convenient for everybody, I hope. But I'll make some plans. I'll try to get back to you by Friday, but it might be before, by Tuesday next time. So anyway, thank you all. We'll see you on Tuesday.